Hello, my name is Nikan Kupaya-Bizani, and I recently graduated from the University of Wisconsin-Madison with a BS in Physics and Astronomy. I've been accepted to Wisconsin's graduate program for atmospheric sciences. Today I'll be presenting some of my work on investigating potential seasonal effects on geocoronal hydrogen emission. I'm conducting this project along with my mentor Susan Nossel and my colleague Ariana Ranabat. I'll begin by giving a brief overview of our research, detail some background information, take you through our process of data collection, analysis, and calibration, and finally showcase what is in store for the future of our work. We're investigating how hydrogen Balmer alpha emissions vary with shadow height, season, and the solar cycle. Data from the Wisconsin H-alpha mapper FabryPro was utilized when it was in Cape Peak, Arizona. This device recorded emission data that we used in order to construct plots showcasing the relationship of hydrogen emission intensity and shadow height. Currently, my efforts are focused on investigating how hydrogen emission variability is affected by seasonal changes. I'll be plotting the summer months of each year and comparing them with the existing winter data. This research may give us a better idea of how atomic hydrogen behaves in the thermosphere. Furthermore, understanding natural variability will grant us the ability to detect potential anthropogenic influence on the upper atmosphere. Now I'll go into some of the background of our research. So the sun goes through natural cycles of high and low solar activity. This is what's known as the solar cycle. The period of the cycle is about 11 years, and the WAM has taken data at a time of solar maximum, 2000-2001, and a solar minimum, which is 1997 and 2006. And notice the dramatic change in sunspot number from 1990 to 1996, from 1996 to 2001, and from 2001 to 2009, and so on. According to this graph, we're currently residing at a solar minimum year, where the number of sunspots are at a minimum. So now I'll go into the hydrogen Balmer alpha emission. So this type of emission is at a wavelength of about 656 nanometers, which tends towards a red-light color in the visible spectrum. Hydrogen atoms are excited by solar radiation, which is then followed by a spontaneous drop in energy. For the Balmer alpha transition in particular, the electron is initially positioned in an n equals 3 shell, and it loses energy and transitions to the n equals 2 shell. This transition results in the emission of H-alpha light that is observed by WAM. The FabryPro interference pattern is then converted into a spectrum that we utilize in our data analysis. I'll also introduce another parameter. This is the shadow height or shadow altitude. And this is the length denoting the vertical distance from the Earth's surface to the edge of its shadow. So in the diagram on the right there, you can see that this distance is denoted by the blue line. Now I'll shift into covering some details about data collection. So the WAM FabryPro, which is pictured on the left, is used as a means to collect hydrogen emission data from the upper atmosphere during the nighttime. The data is then converted to a spectral profile, and you can see one of those profiles pictured on the right there, that can be used for analysis. The spectra are uploaded to a directory, and then eventually they're accessed using the Unix operating system. So our step-by-step process of data analysis is as follows. We obtain the spectral data from WAM that was accessed through the Unix operating system. The data is then fit using the Voigt fit spectral fitting code. This fit grants us with a numerical value for the area under the curve. This value is then compared with a nebular calibration source to calculate the emission intensity. And as mentioned before, the header is used to obtain variables such as zenith angle, shadow height, exposure time, and those parameters. And note that in general, the header gives information about how observations were made, including the time of observation and pointing direction. And then lastly, data is entered into an Excel spreadsheet, and then using Python, a plot is constructed displaying hydrogen emission intensity as a function of shadow height. So now diving into calibration of this data, the Balmer alpha emission intensities in the upper atmosphere that are required by WAM are calibrated with respect to the Balmer alpha emission intensities of the North American nebula, which is pictured on the left right here. We then use the following equation to calculate the intensities in the geocorona. This factor allows for the scaling of the intensities in a way that's meaningful for data analysis. Additionally, data with zenith angles of less than or equal to 50 degrees was used in order to reduce the impact of atmospheric scattering on atomic hydrogen emission. This figure showcases one example of a finalized plot and is a work in progress. I plan to analyze WAM observations from additional months during 2006. I then plan to compare the 2006 solar minimum observations with those from the year 2000 during near solar maximum conditions. The plot displays intensity in Rayleighs as a function of shadow height in kilometers for 3 months in the year 2006. Please note that the legend has the dates listed in the following format: year, month, and day. We can see that hydrogen Balmer alpha emission is most intense just outside of Earth's shadow. Furthermore, as shadow height increases, we observe a dramatic decrease in the intensity. I am now working towards adding more months to this plot and also plan to construct similar plots for other years. So when we carry out research, it's important to acknowledge why all of this matters and, in general, how it's contributing to the science in the field. This research is being conducted with the hope of contributing to the understanding of atomic hydrogen behavior in the thermosphere and exosphere. Furthermore, understanding natural variability may also assist us in isolating potential markers for climate change impacts on the upper atmosphere. Other similar studies include work by Gallant et al. In 2019, which showed that the dusk-dawn difference in Balmer alpha intensity depends on season. Our future plan is to extend our focus to the southern hemisphere. Since the WAM instrument has moved from Kitt Peak, Arizona to the Coquimbo region in Chile, we will now be able to analyze data from another geographic location to complement our findings. We're in the process of analyzing data from solar minimum and maximum conditions and different seasons. This is done to investigate whether there's a seasonal dependence of hydrogen emission response to changes in solar activity. In addition, we plan to compare WAM observations taken from the southern and northern hemisphere. I will then attempt to couple these new findings with the effects of seasonal variability to gain an even deeper understanding of this upper atmospheric phenomenon. Thank you very much for listening. We are grateful for support provided by the National Science Foundation and for funding from the University of Wisconsin-Madison Physics Department. If you have any questions, feel free to contact any of us via email.